310 is kind of fun in a sadistic sort of way. No, it's related rates. This is where we get to look at the applications of what we're doing. So in this section, we look at problems that ask for the rate at which some variables change when it is known how the rate of other variables or related variables change. So the problem of finding a rate of change from other known rates of change is called a related rate problem. This is the strategy we're going to be using whenever we do related rate problems. First thing you want to do is draw a picture. Please draw a picture. And name the variables and the constants and use t for time. Assume that all variables are differentiable functions of t. Here we're going to be taking the derivative with respect to time. A rate of change implies time is your variable that you're taking the derivative with respect to. Number 2, write down the numerical information. Label everything you can. Write down what you're asked to find. And then write an equation that relates to the variables. You may have to combine 2 or more equations to end up with all the variables in the right place. And then take the derivative with respect to time. Any formulas you need for these problems, you can find them in the front flap jacket of the book. There's a whole section on geometric shapes, 3-dimensional, 2-dimensional, and all of that good stuff. On a test, I would give them to you. So here's our first problem. It says sand falls from a conveyor belt at a rate of 15 cubic meters per minute. So I know my distance is measured in meters and my time is measured in minutes because that's this rate of change. I also know this is the rate of change for the volume because these are cubic meters in the units. See, I knew a lot just by looking at that one number. So the change in the volume with respect to time is going to be 15 cubic meters per minute. Just reading this. It falls onto the top of a conical pile. So I've got a right circular cone here. Okay. The height of the pile is always 3/8 of the base diameter. So whatever the height is right here of this cone, it's always going to be 3/8 of the base diameter, which is 3/4 of the radius, right? Just drawing a picture as I go along. So if this is the radius, this is the height is 3/4 of the radius, right?
Showing that, please.
Nope, I think it's 3/16. Hang on. The height of the pile is 3/8 the diameter. The diameter is twice the radius. No, I'm right. It's 3/4 the radius. There we go. This right here came from this sentence. The height of the pile is always 3/8 of the base diameter. We okay with that? All right. How fast are the height and the radius changing when the pile is 7 meters high? So we're looking for dH dt, the change in the height with respect to time, and dr dt, that's the derivative of the radius with respect to time, when when the h is 7, when the height is 7, right? We okay with that? I know that I've got something going on with volume as well, right? So what I'm going to do is I got to start with an equation. Well, here's the equation we're going to start with. The equation for the volume of a right circular cone is volume is equal to 1/3 pi r squared h, right? I can use this information to turn this into an equation with only one variable. Would you agree? Okay. My variable I want to be h because I'm told what to do when h is 7. I want the h in the problem. This to me means I want h to be a variable. So I don't want to replace h here with 3/4 r. I want to replace r with 4/3 h. Right? This is the same thing as r equals 4/3 h. Would you agree with that statement? Okay? So then I can take this value right here and I can replace r with it in this equation. You with me? That way I have an equation with only one variable. So now I have the volume is pi over 3 times 4/3 h cubed times h. So far so good? If I do something that you don't agree with or you don't follow, speak up, please. Because it's not supposed to be, it's squared. Oh. Sorry. Okay, so let's clean this up now. We have volume is equal to, when I square 4, I get 16 pi. 3 squared is 9 times 3 is 27 h cubed. That's where I was headed. My brain just got a little ahead. Okay? This is the equation that I'm going to differentiate now. Now take derivative. Four squared is 16. 3 squared is 9 times the 3 that's already down there is 27. Now we're going to take the derivative with respect to, or WRT means with respect to time. So what we end up with is dV dt, the derivative, the change in the volume with respect to time, is equal to 16 pi over 27 is a constant. Now we take the derivative of the h cubed, and that's going to give us 3h squared dh dt. Right? I'm taking the derivative implicitly because the variable that I'm taking the derivative with respect to here is time. Because I'm looking for a rate of change. Rate of change is a change in time. So what am I going to plug in for dV dt? You sure?
Yeah.
Oops. Don't want that. So now I'm going to get 15, because that was dV dt, equals, this 3 is going to cancel with this 3, leaving behind 9. So this is going to be 16 pi over 9. H is going to be what? dH dt. Because remember, when H was 7 was part of this. We're finding dH dt and dR dt when H is 7. Yes, sir?
So we went from B to dV dt.
Because we took the derivative with respect to time.
But why didn't we use the product rule to get it?
Where would you have a product? That's just a variable.
Oh, it is.
This is just a constant times a variable.
I saw pi.
I know, you were thinking pi. By the way, because you're here now and I like you, I'm quite fond of putting something like this on the test. Don't fall for it. That is not 3 pi squared. What is that? 0. That's a constant.
The derivative
of the constant is always 0?
Yes. That one I'm fond of as well. It will be multiple choice. That one. When the derivative of that is 0. E is 2.71828. Just like pi is 3.14. That's right. I like y'all. I'm warning you. I'm deleting this part of the video. So if you're not here, you don't get that information. And I'm telling you, I will do it. Don't fall for that one. So, I did warn, well, I only warned a few people last time who stayed late. So, now we have 15 equals, I don't know, give me numbers here. 16 times 49.
784.
Pi over 9 times dH dt. How do I get dH dt? Multiply by the reciprocal. So we end up with dH dt when h is equal to 7 is going to be equal to 15 times 9. What's 15 times 9? Over 784 pi. So that's 139, you said? 35 over 784 pi, which is approximately what?
That's a decimal.
Yeah, I know it is.
Okay, 0.5.
Did you put the denominator in parentheses?
I did not.
Then you're not going to get the right answer.
You sure?
Yeah, it's very small. What are the units? Okay. All right. We found dH dt. How am I going to find dr dt? When h equals 7 and dH dt equals 0.0549. Well, remember that equation that looks like this? R is equal to 3/4 h. We can take the derivative of this with respect to time. And when when h is equal to 7, we get dr dt is equal to 3/4 of 135 over 784 pi. And that's going to be what? 0.01 something. What?
You got 0.04. I got 0.04.
Use your calculator.
Can't do that.
You can't, because you got to put the 3/4 in parentheses.
Aww.
Or you can use 0.75.
Okay.
And you get
How about this one?
0.0548. Oh, I didn't multiply by 3. You're right. 0.0411. I didn't multiply by 3. And what are the units here? Meters per minute.
No.
It's the units of the radius, which is meters, divided by the units of time, which is minutes. Right? So we need an equation that we can take the derivative of with respect to time that relates only the variables that contain the information that we know. We knew we wanted h because we were told the value of h. The constant that we knew for our rate of change had to do with volume. That gave us a clue that we needed an equation for volume. Fortunately for us, they had an equation that related the height and the volume. Okay? Next problem.
So what's our final answer to that question?
We were asked to find how fast the height and the radius are changing when the pile is 7 meters high. So when the pile is 7 meters high, I'll actually formally state this. When the pile is 7 meters high, the height is changing at, well, let's do radius. Um, 0.0411 meters. Change that to centimeters. How do you change it to centimeters? Well, it's 4.1 centimeters per minute. And the radius, and the height is changing at 0.0548
Why would we change the radius to centimeters?
meters per minute, which is equivalent to, because 5.2 centimeters per minute makes more sense than 0.0548 meters.
Okay. What is it?
To change for your units from meters to centimeters, you just move the decimal to the right 2 places.
Would it be 5?
5.
Or yeah, 5.
Sorry, I was rounding and I don't know where the 2 came from. Okay, centimeters make more sense for measuring because on a meter stick, I can find centimeters really easy, but to find 0.054 meters is cumbersome at best. Next problem. On a morning of a day when the sun will pass directly overhead, the shadow of a 72-foot building on level ground is 21 feet long. At the moment in question, the angle the sun makes with the ground is increasing at a rate of 0.25 degrees per minute. At what rate is the shadow decreasing? Remember to use radians. So as the sun comes up, the length of this shadow, or the angle made with the shadow in the building here, is going to get smaller. We're going to use the fact that tangent theta is equal to opposite over adjacent. Here's the angle theta. So what we know right here, this rate of change is what? We know d theta dt is equal to 0.25 degrees per minute. A quarter of a degree per minute. That's the rate of change. At that moment, we know that the height of the building, so when we draw our triangle here to draw a picture of the problem, at the moment that this 72-foot tall building has a shadow of 21 feet, we know the value of the d theta dt. So when x is equal to 21 and y is equal to 72. So the trig function that we're going to use to set this up is tangent theta equals y over x. Okay? Now, rather than have an x and a y in this problem, the 72-foot tall building isn't going to change, is it? We're going to use this as a variable right here. So tan theta is equal to 72 over x, right?
Mm-hmm.
So tangent theta is equal to 72 x to the negative 1. What is it that we want to know? At what rate is the shadow decreasing? That is dx dt. Yeah, that's a W. 10. Okay, so that means that we're going to have to take the derivative of this equation with respect to time. Can we do that? Okay, so the derivative of tangent is ooh, I just had a stroke of genius. Before we do that, let's rewrite this function. How can I get the theta by itself? Don't divide by tangent. Take tangent of both, tan inverse of both sides. Right? So that we have the equation theta equals tan inverse of 72 over x. Do you remember the tan inverse derivative rule? 1 plus u squared du dx. Yeah. Yeah. So, right here we're going to recall the derivative with respect to x of tan inverse u is equal to 1 over 1 plus u squared du dx. We okay with that? Can I use that? I just think this is going to be easier because we actually know d theta dt. And guess what? When we take the derivative with respect to time of this function, we get d theta dt equals, the derivative of this is going to be 1 over 1 plus the angle squared du dt. The derivative of this angle is going to be negative 72 x to the negative 2. Well, that's over x squared. I'll write it like this. X to the negative 2. dx dt. Geez, there's another one. So we have d theta dt is equal to negative 72 over x squared times 1 plus 72 squared. What's 72 squared? I don't know either. 72 squared over x squared. Now I can distribute this x squared just to make life easier or harder. I don't know which. What's d theta dt? 0.25 degrees per minute equals negative 72 over x squared plus 72 squared dx dt. Do I know a number for x that I can plug in?
So, 21.
Right?
Yeah.
Because it was when the shadow was 21 feet long. So this ends up being, how do I get the dx dt by itself? I distributed the x squared to the 1, that gave me the x squared, and to this term where the x squared canceled out with the x squared in the bottom, and that gave me the 72 squared. Now, how do I get the dx dt by itself? Because that's what I want to find, the rate at which the shadow is changing. I'm going to multiply both sides by the reciprocal. So this is 0.25 times 21 squared plus 72 squared over negative 72. That's dx dt. This is why God gave us calculators. What's your parentheses? I don't know what this is. So it's 0.25 times, open parentheses,
I'll let somebody else tell you the answer.
21 squared plus 72 squared, close the parentheses, divided by negative 72. What's your calculator?
That's the answer I got the first time. But you can go
0.25 times 21 squared plus 72 squared divided by negative 72. Ooh. There was something already there that I didn't pay attention to. 21 squared plus 72 squared divided by negative 72. I get negative 19.53, which is what you got.
See, when I just keep one piece and press enter and do that piece.
It's negative 19.5. We'll just say negative 19.5. And then what are the units going to be? Feet per?
I thought it was inches.
Ooh, no.
No.
This was degrees per minute. This is measured in feet. So the units...
Express your answers in inches per minute at the end of it.
What was wrong? We didn't use radians. This is not 0.25. This is 0.25 times what?
Oh.
It's 0.25. We got to change it to radians. How do you change degrees to radians? Times pi over 180. Times pi over 180. So take that answer, multiply by pi, and then divide by 180.
Take that answer, multiply by 5.
Just say times pi divided by 180.
Ooh, negative 0.34.
Negative 0.34. This is feet per minute. But if we change the feet to inches, we multiply by 12.
Yeah.
And we get y dx dt is equal to 4 inches per minute. Right? Convert feet to inches. Any questions? No? You need true. Well, that's a statement, not a question. All right, next example. Right triangle trig. We like. All right, it says a 13-foot ladder is leaning against a house when its base starts to slide away. So here's the ladder. It's 13 feet long. That distance is not going to change. The base starts to slide away. So here we go. The base is sliding away. By the time the base is 12 feet from the house, so once this is 12 right here, 12 feet, the base is moving away at a rate of 5 feet per second. Well, guess what that is? That is dx dt. That's an x. Just looking at the picture here. So dx dt is 5. Question A, what is the rate of change of the height of the top of the ladder? So we're looking for dy dt. So we want to know dy dt for question part A. Okay, can we do this? We have to assume that this wall or the house is perpendicular to the ground, and unless we're at the Leaning Tower of Pisa, is a fairly safe assumption. Okay? We need a relationship between our variables x and y. Oh no, let's not use trig if we don't have to. Let's go for the Pythagorean Theorem. Are y'all okay with that?
Yes.
Okay, so we know that x squared plus y squared equals 13 squared. This is from the Pythagorean Theorem, right? So, when we take the derivative with respect to time, we end up with 2x dx dt plus 2y dy dt equals what? Wasn't trying to trick you. I just want to see if you remember the derivative of a constant is 0. Okay? All right, we know dx dt, right? We also know a number for x, don't we? So now at this point we're going to plug in, not pug in, but plug in the numbers that we know. All right, so we have 2 times 5, because it said when the, not 5, 12. When the base of the ladder is 12 feet from the house, we're falling at this rate. So 2 times 12, what's dx dt? 5 times 5 plus 2 times y, dy dt is what we're looking for, equals 0. Well, do I know a number for y? I can only have one unknown in the equation. Isn't this a right triangle? When x is equal to 12 and the hypotenuse is 13, don't we know what y is? It's 5, right? Using the Pythagorean Theorem. Okay. Can we solve this equation then for dy dt? This ends up giving us 120 plus 10 dy dt equals 0. Subtract 120 from both sides. So if we divide both sides by 10, we get dy dt is equal to negative 12. What are the units here? Feet per second. So when the base of this ladder is scooching out at 5 feet per second, when it's 12 feet, the top is going down. That's a direction. The negative's a direction. 12 feet per second. Okay?
Take it less than a second.
Oh, yeah. Yeah. And if you've ever been at the top of that ladder, you know it takes less than a second. All right? That's the adrenaline. Part B, it says at what rate is the area of the triangle formed by the ladder, wall, and ground changing then? How do you find the area of a triangle? 1/2 the base times the height, right? X is the base. Y is the height. Right? Product rule. So we're going to look at this then, and we're going to take the derivative with respect to time. Not a big deal. dA dt is equal to 1/2. It's the first times the derivative of the second plus the second times the derivative of the first. Right? Well, when I take the derivative of x, I get the 1/2. I knew that, so I just stuck it in front. So, now we plug in the numbers that we know. Alright, so what numbers do we know? We're looking for dA dt. We know x, we know dy dt, we know y, and we know dx dt. Oops. Tell me what all these numbers are. X is 5, dy dt is -12, y is 12, and dx dt is 5.
I think X is 12, does it matter?
Yeah, it does matter. X is 12. Yeah, that matters big time.
Y is 5.
And y is 5. Yes. Big time matter. I just forgot. Getting hungry. Getting a headache. Okay, so looking at this then, we have dA dt, the change in the area with respect to time, is going to be negative, that's 146 times 12, 72. Is that right? Plus half of 25 is 12.5. Is that right? So this is going to be negative 69.5. Is that right? Negative 72 plus 12.5.
Mm-hmm.
And then what are the units here? Yeah, that's right. 59.5. Thank you. Right here. Why is it negative 12? It's what we found in part A. Yeah, that we needed to know that before we could do part B. All right. So this triangle is getting smaller at a rate of about 60 square feet per second. All right. I don't know why you would want to know that, but there you go. Part C says at what rate is the angle between the ladder and the ground changing? Now we're going to use our trig. So at what rate is the angle between the ladder and the ground changing? I'm going to draw a picture here. Here's theta. This is x, this is y, this is 13. We need a trig function. I like tangent, except I can't use tangent. We can use cosine or sine. Which one do you want to use? Sine. I like sine. So we know that sine theta is equal to opposite over hypotenuse. Is that right?
Mm-hmm.
So theta is equal to sine inverse y over 13. Is that correct? Take the derivative with respect to time. And when we take the derivative with respect to time, we end up with d theta dt is equal to, now I got to remember this inverse. The derivative with respect to x of sine inverse u is going to be 1 over the square root of, was it 1 minus u squared or u squared minus? Thank you. 1 minus u squared du dx. So we got to recall this in order to do the derivative. So this u is y over 13. So here we go. So this is going to be 1 over the square root of 1 minus y over 13 squared. And then the derivative of that is 1/13, right? The derivative of the angle of u here, not the angle, but the argument. And then we have, I took the derivative here with respect to y, so that's dy dt. Now we plug in numbers that we know. So we gotta, we're almost done. Y'all signed up for summer school classes, not me. So you get d theta dt equals 1 over the square root of 1 minus, what was y, 5? In the original problem, x was 12, so y is 5/13 squared times 1/13 times, and dy dt was negative 12. Y'all wrote the problem down, right? Mm-hmm. On your calculators. What's 169 minus 25? Ooh. 169 minus 25. 144. This is going to end up being 12, I believe. 1 divided by the square root of 1 minus 5/13 squared. Now, math, enter. 13/12. This right here, if you plug that into your calculator, you end up getting 13/12. So d theta dt is equal to 13/12 times negative 12 over 13. We end up with negative 1. What are the units here? Radians per second. Remember, whenever you do calculus with the angles, those angles have to be measured in radians. Right? Right. We're done. The videos